I'll start the recording. So it's my great pleasure to introduce David Huse from Princeton University. A few words about David. He did his PhD in statistical physics with Michael Fisher, and that was at Cornell. And then he spent, about 15 years, David, at Bell Labs before becoming a full professor at Princeton University, where he's also a member of the Princeton Center for Theoretical Sciences and a professor of mathematical physics. David has a career that's extremely rich with different kinds of physics that he's done, which ranges topic as diverse as the spin glasses, the theory of randomness, the rare effects, and something maybe what more familiar to people who do condensed matter experiments, including the superconductivity, frustrated spin systems, magnetism. Today, David is going to tell us about a subject that I first learned about when I bumped into David at a Lezouche summer school. I believe this was around 2006. And NPL was just about starting there. And I remember you, David, were walking around, and I think Vadim Oganessian was your partner in conversations, and you were discussing MBL, and this was at the time way above my head. But
brand new then.
That's right. So we'll hear today, what happened in the field of MBL since those days, right? Another 15 years have passed. But before we start, let me also say that David is a recipient of many prizes. He's also the member of National Academy of Sciences and then Academy of Arts, Association of the Advancement of Science. And with this, without further ado, David, the floor is yours.
Okay. So actually, to be more precise, I'm not just going to talk about many-body localization. I'm going to talk about quantum thermalization, which is what happens in most systems. And many-body localization is a particular case where it doesn't happen. And so actually, given that this is a colloquium for a general audience, I'm going to spend most of my time on the more basic fundamental thing that happens in most systems, not the ones which are localized, okay? And this is something that you should have had a lecture on in your statistical mechanics course, but a good understanding of it is only quite recent, and so it's not yet really in the textbooks. And so this is like what I'm giving you is a class that you should have had when you were in grad school, but you're getting it today. So it's about some fundamentals in both quantum many-body dynamics, which has become a very active subject in research these days, as well as quantum statistical mechanics. And why has this become a very active subject? It's basically due to two closely related things that happened. One is atomic physics became many-body physics. So there were a lot of new questions in many-body physics that could be addressed in the laboratory and examined in the laboratory that just really weren't particularly accessible at all in other kinds of quantum many-body physics problems like in condensed matter. So a lot of nice new questions. And then not unrelated, there's this effort to build quantum information processing systems, which of course are many-body quantum systems, and we'd like to understand rather generally what many-body quantum systems do because we're trying to build them. Okay, and so an interest in sort of generic questions about many-body quantum dynamics, has become a big topic of research for a big community of people in the past 15 years or so, due to these things. Okay, so this is basic stuff. So it's like back to your basic statistical mechanics course. So what we're going to consider is an isolated system, quantum. It's going to be quantum, many-body system. Now, it could be a solid or a quantum field theory, but more practically, the kinds of questions we're asking, we can investigate them. Ultra-cold atoms was, what really got this started. Various systems of qubits, spin systems, so quite general. And so it's isolated. So by isolated, I mean no external environment. If there is anything you would call an environment, it's internal. So if you want to study a system interacting with its environment, let's just put the environment as part of our system, right? And then just put a box. So this box is what we're talking about. It's not coupled to anything outside. It contains many degrees of freedom, some of which might be something you would call the environment. We just put a little bit of it in there if we want to, just to see what's going on. Because it's isolated, it has its dynamics is given by its Hamiltonian. Now we could have some external, not environment, but a drive that gives the Hamiltonian some time dependence in a classical way. So I'm going to consider possibly time-dependent Hamiltonians, often time-independent, but I want to be general right now. Okay, and then we're going to start this in some initial state that's out of thermal equilibrium, and we're going to ask, does it go to thermal equilibrium? Thermal equilibrium, which is what you assume in your statistical mechanics course. You take a closed system, many degrees of freedom, wait, it goes to thermal equilibrium, right? That's what you assume. But this is a non-trivial question, right? And we've learned a lot about it, and we know about systems for which it's not true. Okay, and to make that question well defined, you have to take the limits of a large system and long time. Now that may sound like, oh, that really makes it just an academic because you're never really in this limit, but the behavior I'm talking about, it comes out for surprisingly small systems and surprisingly short times that you can investigate these questions. So once these questions were formulated and you start looking at them on computers, on size systems that you can simulate on a classical computer, the physics I'm telling you about, it, you know, if you choose the right models, you can really see it. So we're thinking about these limits, but the behavior I'm going to talk about is apparent without really getting strongly into those limits. Okay, we're not going to talk about any special cases of the Hamiltonian like integrable systems or non-interacting systems, or what the recent thing is quantum scars, which is another special case, but I'm not going to talk about those. I want to talk about generic systems, it's quantum chaotic, or it's many-body localized when I get to that. Now what we're going to do is we're going to start our system in an initial state, and it's going to be observably out of thermal equilibrium. And I have to say so I'm underlining words that need better definitions, or I need to say a little bit more about what I mean by the definition. So I'm going to say something about what I mean by observables in a bit. So the initial state is observably out of thermal equilibrium. And then we ask the fundamental question, which is, if we wait and the system is big, does this dynamics, which is just a reversible quantum dynamics given by this Hamiltonian, does it bring the system to thermal equilibrium? As you would assume in your statistical mechanics course. And if that is true, which it is for most systems, although there are exceptions, that's what we call thermalization. That the system under its own dynamics goes to thermal equilibrium. You don't need an external bath. The system is being a bath for its own subsystems. So a system that goes to thermal equilibrium on its own, it itself is acting as a bath for its parts, right? And then one case where the answer to this question is no is many-body localization. So many-body localization is abbreviated MBL, and that's the many-body version of Anderson localization, both many-body interacting high temperatures. So it's not ground states. We're not talking about ground states at all. We're talking about highly excited states, dynamics. And when a system is many-body Anderson localized, it fails to be a bath for itself. So there's no, although the system has many interacting degrees of freedom, there is no bath. And it gets stuck near the initial state. So that's the agenda. So I'm going to mostly talk about this, but get to this at the end, time permitting. And I like getting questions during the talk. So just unmute yourself and yell out questions when you feel like it. Okay, so I'm going to focus now on thermalization. I give a few of the important early papers. So there's this exact diagonalization paper who first noticed this effect. 1987, computers were rather early in the game. And so they had a chain of 7 spins. But if you choose the right Hamiltonian that's strongly quantum chaotic, and it's surprising looking back at that paper how they knew how to do that, you can see a lot of the physics we're talking about. 7 spins. So that's a Hilbert space of 128 states, right? That's a pretty small matrix, right? But you can see the physics I'm going to tell you about. At least they saw some of it, right? It was talked about more seriously by Deutsch and Srednichi. So this was in the era of the study of quantum chaos, but mostly of systems of a very small number of degrees of freedom. But these people were starting to think about many degrees of freedom and what quantum chaos would mean in that case. This is before BEC, ultra cold atoms BEC. The work got kind of forgotten. But then cold atoms came along. People started putting atoms in optical lattices, making these strongly interacting systems out of ultra cold atoms in the laboratory. And then there was this paper by Marcus Riegel and collaborators, 2008, which really brought this whole issue back and showed how, it's really very relevant to experiments that were being done on ultra cold atoms that could easily be done. So this was a very important paper of sort of just bringing the subject to the attention of all the people doing this kind of work. And since then, it's been a very active subject. Okay. Some of these words look innocent, but one needs definition. So what is thermal equilibrium? It is well defined in the limit of a large system, what we call the thermodynamic limit. And so I'll try to at least outline the definition. There's something we've learned about it, which is more than what you hear about in your classes. So thermal equilibrium is any state. Now, a state of a many-body quantum system, even if it's a pure state, it's a wave function. That's a probability distribution. So a single quantum state really is itself an ensemble, right? Because everything has probabilities in it, right? So it's any state, which could be mixed or pure, and any quantum state really is in some sense an ensemble because quantum mechanics is probabilistic. So any state that is equivalent to the standard statistical mechanical ensembles, right? And so the microcanonical ensemble of fixed energy or the canonical ensemble of fixed temperature, and you've learned that these are equivalent in your statistical mechanics course, and that's what I'm going to review. But the equivalent thermal equilibrium ensembles that you've learned about in statistical mechanics is just a tiny set of ensembles. There's an enormous set of other ensembles that I'm going to tell you about. Basically, any initial state which can go to thermal equilibrium will at long times go to thermal equilibrium, and that will be a thermal ensemble. But because the dynamics is reversible, that ensemble contains all the information about the initial state. So for every out of equilibrium initial state that can go to thermal equilibrium, there is an ensemble that it goes to at long times, which is a thermal equilibrium ensemble. Okay, so what do we mean by equivalence of the ensembles? And I was in the middle of writing this when I looked at my watch and realized so same probability distributions of observables. So if you have two ensembles or quantum states, and you ask for that state, what is the probability distribution of a given observable? If I measure it, what would be the probability distribution of the results? And the results are independent, are the same for those two states, and the same as the standard equilibrium ensembles. Those are all equilibrium ensembles or equilibrium states. I call them thermal states. So a thermal state is a state which is equivalent in this sense to the standard thermal equilibrium ensembles. Okay, but here's another word which we have to say, oh, what are the observables, right? Okay, and there's a point to be made here. Okay, so again, so this gets to your quantum mechanics class, right? So you learned in your quantum mechanics class that all observables are Hermitian operators. And that's fine. But your professor might have also told you that all Hermitian operators are observables, which is true if your system is a finite system. So if you're talking about few body quantum mechanics, which is typically all you ever do in your quantum mechanics course, till you get to field theory or something, people would often say, yeah, all Hermitian operators are observables, but that's not true. So in the limit we're talking about, so in the limit of an infinite system, almost all Hermitian operators are not observables. And this, for today's discussion, is an important point. And let me just illustrate that with an example. So let's say we have n qubits. I'll call them spin 1/2. I have n spin 1/2 or qubits. Okay, now with n spin 1/2, as you know, the Hilbert space is 2 to the n, is spanned by 2 to the n basis states. Right? Each spin could be up or down, and choose that basis. So we have 2 to the n basis states, but we have 4 to the n operators. Because for each spin, you have 4 Pauli operators, which are the identity and the x, y, and z Pauli operators. So there's 4 Pauli operators for each spin, and an outer product of a Pauli operator on each spin is an operator on the full system. So 4 operators per spin. 2 states per spin, 4 operators per spin. 4 is the square of 2. 2 times 2 gives 4. Now, in the limit of an infinite system, almost all of these operators involve an infinite number of spins, right? And an operator that involves controlling and measuring an infinite number of spins is not an observable. So an observable is an operator that acts only on a finite number of degrees of freedom, so that one could actually observe it in the laboratory. So that's what I mean here. So I want to make that distinction in the limit of an infinite system between observables, which are operators acting only on a finite number of degrees of freedom, and all the other operators, which almost all of which involve an infinite number of degrees of freedom in this limit, right? Okay. So when we say 2 states are equivalent, they have the same probability stability distribution on the observables, that's just a very small set of all properties of those states you could look at. And that's why there are so many states which are equivalent thermal equilibrium states, because we're not asking so much when we ask them to be the same only on the observables, because that's a set of measure zero of all the operators.
So David, may I ask, so Matt Forster has a question.
Yeah.
Matt, could you unmute yourself?
Right. Yeah, I mean, I think so you're basically saying that you want observables to be local. Presumably you mean local operators of some kind.
Well, local in a, not strictly local in space, a small number of degrees of freedom. So if you do, like say if you do coherent X-ray scattering with a large coherence length, this is sensitive to the 2-point function out to distances of the coherence.
Sure.
Your beam.
But that's local in momentum.
And that's fine. It's a 2-point operator.
Right.
Even if they're very far apart, that's an observable. We know that because people do this in the laboratory.
Right. Mm-hmm. I mean, in the canonical sense of quantum field theory, we think of, multi-point correlation functions up to some finite number of points.
Yeah.
I guess that's maybe what you have.
Exactly. Right. Mm-hmm. But so it's, yeah, and I'm not insisting about local in the sense of nearby to each other.
Right.
Mm-hmm. David, and maybe if I may, one question from me. When you talk about the distribution of observables according to the thermal ensemble, is it the same as making a statement about eigenstate thermalization? That is that the eigenstates themselves, were you to solve for them,
well, that's
would be distributed with the Boltzmann distribution.
So far, I'm not talking about eigenstates. I'm just talking about states.
Mm-hmm. But let's say you had access to eigenstates, because that's how I know how to compute an expectational observable. I would trace it with a density matrix, which in this case would be.
Yeah. So the eigenstate, right? When you say eigenstate thermalization, what do you mean by thermalization? The eigenstate thermalization hypothesis is the hypothesis that all eigenstates are thermal in the sense of this definition.
Okay, yeah, that's what I wanted to clarify. Okay.
Yeah, but just like almost all operators. Let's see, where did they say it here? Almost all operators are not observable because it's an infinite order thing. Similarly, the eigenstates themselves, they're not really accessible things in the limit of an infinite system. So that's why I'm going to talk about eigenstates, but it's better not to talk about eigenstates when you take this limit because they're not really accessible things, right? You have dynamics, you have properties you can measure, but the eigenstates, we have them theoretically, but it's something that's out of reach in this limit, right? So that's why I haven't mentioned them yet, but I will. Okay, so let's consider, so here's our system again, and let's consider a small subsystem, which I'll call S, and the rest of the system I will call B, which is the complement. So this is the degrees of freedom in some subsystem. They don't have to, like I was just saying in response to Matt's question, they don't have to be near each other in space. It's just some set of degrees of freedom. I've drawn it as a circle here, as if it was near to each other in space, but that's not essential. It's just a small set of the degrees of freedom, and this is all the other degrees of freedom. And the Hilbert space of the full system is the product of this Hilbert space and this Hilbert space. And the complement of my small subsystem I'm calling B because we're basically asking, is this acting like a bath for this, right? But it's really just the rest of our system, okay? So actually, I should have drawn that on another board because I'm almost out of room. So I'm just going to pull down and erase. And the lights haven't gone out yet. I'm getting nervous. But maybe I'm waving my arms more than usual. Okay, so here's my system again with the subsystem. So this is the full system. Here's a subsystem. Here's the rest of the system. Okay, now in general, if you're talking about a system of many degrees of freedom, not only will you not have eigenstates, you will never have pure states either. You know, preparing pure states in the laboratory is not feasible except for very small systems. So I prefer to talk always in terms of mixed states just to be realistic. Okay, so the state of the system is a mixed state, which I'm going to denote by a density operator rho, or density operator rho. So this is the state of the full system. The full system means my subsystem and the bath. And then we define the state of the subsystem, rho S, is, there it goes. Rho S is the state of my subsystem. So this is an operator just on the degrees of freedom in my subsystem. And this, to get this, we take a trace over the bath, or over all the rest of the degrees of freedom in the full system. So this is a partial trace over those degrees of freedom, leaving these ones untraced over. And we just take a trace of rho. So this defines the state of the subsystem. It's basically taking a trace over all the other degrees of freedom just means ignore those degrees of freedom, right? And so this is the state of the subsystem.
David, can I ask a question?
Yeah, please.
So you said that it's not possible to prepare pure state, but in principle you can prepare, product states, right? For, in principle, arbitrary systems.
You must not be an experimentalist.
No, I am. I mean, but if you have I don't know, a spin system, you can optically pump to.
Don't say that in your paper. When you have 50 spins and you say I made a pure state with fidelity 1, they're going to say,
okay, well, yes, okay, yeah, the fidelity is not 1. Okay, fine.
Exactly. A pure state has fidelity 1.
Okay.
Not 0.999. It has fidelity 1.
Okay, I see.
Yeah, that's what I mean. Pure, I mean pure, not approximately. In your lab, you can prepare states which are approximately pure, but they're mixed. Yeah, that's. Okay, so rho S is the state of the subsystem, and so I can just say what a thermal state is. So a thermal state is for all S, all small subsystems, rho S for this state here. So I'm asking, is my state rho thermal equilibrium? And what I do is I look at all small subsystems, and for all S, rho S is equal to the equilibrium state of rho S, and the equilibrium state of rho S is the same thing, trace over all other degrees of freedom, and just put in one of your standard ensembles here. So let's just put in the Boltzmann distribution. Right, and this will have some parameters, temperature, maybe chemical potential, whatever, to specify the equilibrium. For every conserved quantity in your system, you have to specify a parameter. Temperature or energy density, chemical potential or particle density for every conserved particle, etc. Right, so this is all possible equilibriums, one parameter for each globally conserved quantity. But the number of states of the system which satisfy this in the limit of n goes to infinity is enormous. And for systems that do thermalize, as was said earlier, we have the eigenstate thermalization hypothesis, which it appears that every single eigenstate is a thermal state. It's a fine ensemble. Okay. So some of this was first addressed very early in quantum mechanics by von Neumann. So von Neumann had something that was called typicality, which he showed, which is that in the limit of a large system, amongst all the states of the system, you could consider almost all rho are thermal. So thermal equilibrium states is almost all states. And that's because thermal equilibrium is the maximum entropy, and you maximize the entropy by including everything. Anything that's out of thermal equilibrium has lower entropy, so it must be a very small set of states, because the entropy is just the logarithm of the number of them, right?
And David, almost all here means with measure 1 or something like this?
Yeah, in the limit of n goes to infinity, the fraction that are not thermal goes to 0. The fraction of all, if you consider all possible states, there's a well-defined measure on the set of all possible density operators. The fraction that aren't thermal goes to 0 in the limit of, so it's almost all in the mathematical sense with probability 1, but not that it never happens. That's why the almost, right? Okay, now, and then but you can obviously, you can prepare non-equilibrium states, so non-thermal states. So because of this, because of what von Neumann said, non-thermal states are special. And of course, as I said, we know that they have lower entropy. So the entropy is really about their count. Okay. But we ourselves and the world we live in isn't in a thermal state. It's out of thermal equilibrium. And so because of that, we are quite capable of preparing non-thermal states, just using the non-thermality of the world we live in. So non-thermal states are a perfectly reasonable thing to make, even though they are rare. They are rare, but we live in a rare state. Okay. Now, and then, so systems that do thermalize, so this was mentioned earlier, and I'll just say it again. So ETH is the eigenstate thermalization hypothesis. It's a hypothesis. It can't really be proven for any physically realistic system. You can only prove it for like random matrices and things like that. And that's the hypothesis, which to the extent we can test it numerically, which is pretty well, it appears to be true for most systems, and for systems that do thermalize, it appears to be true, which is that if we have a time-independent Hamiltonian, so this is in the case of a time-independent Hamiltonian, all eigenstates are thermal. Now you might step back from this and say, well, all eigenstates, that's a complete basis. And so any state, any pure state, it's just a linear combination of eigenstates. And if all the eigenstates are thermal, how come all states aren't thermal, right? And the reason is that to produce a non-thermal state, you have to take a particular linear combination of eigenstates with very special properties in order to make it non-thermal. So being out of thermal equilibrium is a type of coherence in the basis of the eigenstates. In order to be out of thermal equilibrium, we need just the right coherence between all the eigenstates such that they add up to produce something that's out of equilibrium. Because all by themselves, they're in thermal equilibrium. The only way they can get out of thermal equilibrium is by being in a very coherent superposition. So being out of thermal equilibrium is coherence, and therefore thermalization going to thermal equilibrium, which is what happens to these systems at long times. Thermalization is decoherence. And because when you have coherence between two eigenstates and the eigenstates have different energies, you wait a while and the phase difference between those two eigenstates rotates just because of e to the I e times t, and that gets them whatever special phase relations you had to produce this coherence. It disappears at long times as those relative phases get shifted. Okay, so thermalization is decoherence. So that's one view on it. Actually, any questions about this before I erase it and start my next?
David, very quick one.
Yeah.
Could we imagine being not in a coherent superposition, but in a distinct ground state, so a pure state separated by a sizable gap from the rest?
Yeah, I should have said that at the beginning. I'm not talking about ground states. I'm talking about highly excited states that correspond to non-zero temperature and non-zero entropy density. Yeah.
Oh, I see. Okay.
Discussions of ground states with gaps. Yeah, one has to. We're just not there. We're way, if there's a ground state with a gap, we're way above the gap in a state that corresponds to a non-zero temperature with a non-zero entropy density.
I see. So the statement about the ETH applies, as you said, to finite energy states. Is that fair?
Well, not really, because if you have a system with a ground state, a unique ground state, which many systems do have a unique ground state.
Yep.
That ground state obeys ETH, right? Because it is the only thermal equilibrium state at zero temperature.
I see.
If you wrote down the Boltzmann distribution at zero temperature, it would be just that state, right?
That's
and so ETH is true in ground states when they're unique. And that's ignoring issues of symmetry breaking, and so there's a bunch of subtleties when you go to low temperatures. How do you deal with symmetry breaking and ordered phases? And you got to, so I'm not only not in the ground state, but I'm actually above any phase transitions, because I don't want to talk about the issues of phase. We can deal with the issues of phase transitions, but it's a distraction from my point today. Okay, so the dynamics, right? So what is the system doing? So the dynamics is just unitary time evolution.
David, can I ask a question here? So I want to suppose the ETH was false. So obviously there's good numerical.
It is for MBL. There are systems for which it's false.
But I guess what I'm trying to understand is, to what extent could we even say statistical physics should ever work if I knew that ETH is false? Does the empirical fact that statistical physics works, that these ensembles we pick work, does that already more or less imply ETH?
No. It's about dynamics. So if you just do equilibrium statistical physics, you don't need ETH.
Right, but if I believe that, the question is, if I have a real system, why should I ever believe a real system is described by statistical mechanics? Can I have that belief but not believe ETH, or are these kind of?
It depends on what you mean by statistical mechanics, right? If you start it out of thermal equilibrium and ask, is it going to go to thermal equilibrium that I can calculate by statistical mechanics? We know there are lots of systems that don't do that. Those Galaxy systems, they remember the initial state.
But I guess what I'm asking is there a generic way I can imagine that happening that does not require ETH? Could I imagine that non-equilibrium dynamics
equilibrium without ETH?
Yeah, because it seems to me that's very hard to imagine. But
yeah, it is. I agree. Right, because ETH, I'm not asking about all the operators, but I ask you about all the observables, right? And that is an infinite set of observables, right? And you know, if your system is anything special like Manybody localized, there will be observables which know about that. Or if it's integrable systems, many of the conserved quantities that are special are observables, and you will see it. Yeah. Right. Okay. So when we do quantum dynamics, you have unitary time evolution, right, which is just given by e to the minus I over h bar. So this is time ordering operator, integral from 0 to t. So this is the operator that gets you from time 0 to time t, h of t. And this is putting everything in time order. It's a unitary time evolution. And because of, so this is unitary. And as a consequence of that, we can just write out the solution. Rho of t at later times is u of t, rho of 0, u dagger of t. It's deterministic on this level, right? On this level, it's deterministic. Of course, this is about probability distribution, so it's not really fully determined. You know, when people say quantum mechanics is determinate, Schrodinger's equation is deterministic, it's kind of silly because Schrodinger's equation is about probabilities, right? But given rho of 0, I can predict rho of t. So that means all information in the initial state about how in detail it was out of thermal equilibrium is still present in the final state, right? Because I could just run this dynamics backwards by putting u dagger u over here, right? Yes. So let me just say the phrase here from what I'm saying. So what is thermalization, right? I said it's a type of decoherence, but it's also a flow of information from observables to non-observables. So if the initial state is out of thermal equilibrium, that means some of its observables were out of equilibrium, and you could observe that. And what happens under this unitary time evolution, if I run long enough and it goes to thermal equilibrium, is those operators that were observable at time 0 evolve in the Heisenberg sense, and they become non-observables in the limit of long time in the final state. So all the ways the system was out of equilibrium at the beginning is hidden. So it's basically hiding. All right, but it's a flow of information in the set of all Hermitian operators, right? Going from observables towards non-observables. And in some sense, this is the second law. There are just infinitely many more of these than these. So if you put information on these guys and just let it go, it's going to go to some operator, and that operator almost, you know, with probability 1 will be non-observable, right? And so that's why you just naturally hide stuff in a system which thermalizes. So that's just another viewpoint on it. Okay, let me, okay, so I'm going to try to get to a little bit of Manybody localization, since that's in my title and I'm using up a lot of time. So maybe if somebody just raised their hand, if somebody has a question about thermalization before I sort of change the topic to non-thermalization.
Hey, yeah.
Yeah, please.
Thank you. This might sound a silly question, but I was just wondering that when you say that the Hamiltonian can be time dependent, but your system is a closed system, meaning there's nothing else outside of the system.
Well, nothing else for it to get entangled with. So if you're driving your system externally by something which is classical or is an appropriately well-defined coherent state of a quantum system, the system can evolve. That can change the Hamiltonian as a function of time. Like if you apply, you know, a very large amplitude radio frequency involving, a ridiculously number of photons in a coherent state, your system's not going to get entangled with those photons. That's just going to drive the Hamiltonian in a time-dependent way, right? So the key is an environment is something you can get entangled with. You can have an external thing that you can't get entangled with, and then that's fine, right? Okay. I hope that's an okay answer.
Couple more
Yeah.
questions, I think. Yeah, go ahead, Altian.
Yeah, go ahead.
Yes, I actually have a question about the something about the invertibility of the thermalization. For the system you have described, for the theory you have described, I find that the portion of the observables to the non-observables should be like for infinitely small for a infinite system, but the absolute number of the observables, should that be like comparable from non-equilibrium to equilibrium?
Well, the observables are all finite order operators. And so basically the number of them is power law in the number of degrees of freedom, right? Say we only include up to, 4 spin operators. So we can do.
Yeah. Just like the fourth
Then
spin.
there's n to the 4th operators, basically.
Yeah, just like the fourth spin operator
Exponential
example.
of the others, right? So they're both infinite, but one is a much stronger infinity than the other. Okay, so now I'm going to go to many-body localization, which is sort of a generic, well, not generic, it is a stable, structurally stable case that does not thermalize. And this is actually there in Anderson's original paper on Anderson localization, 1958. If you read the beginning of this paper from today's point of view, you can see he was working on many-body localization, and then he made some approximations to make it simpler. But the problem he was working on was interacting spins doped into a semiconductor. It was a many spin problem, just like the kinds of problems we're working on today. But you had to wait, 40 some years before other people understood what he was trying to do. May he rest in peace. Okay, so most systems do thermalize, but some are Anderson localized or many-body localized. And so let me just, in the few minutes I have, say a little bit about many-body localization. Okay, so a trivial case, but it's a useful case of many-body localization is this Hamiltonian, a bunch of spin and halves. And I'm going to call this H naught because I'm going to add some corrections to it. And we just have a bunch of spin and halves, n equals 1 to n. And each one is in a field. And the field is coupled to the spin. And that's it, no interactions between the spins. So this is just a bunch of spins, each in their own field. All the fields are different in magnitude, let's say. They're just essentially random. What are the eigenstates of this? It's just 2 to the n eigenstates. Each spin is either aligned with its field or opposite to its field, right? None of those are thermal except for 2 of them. The ground state, where they're all aligned with the field, like we were saying earlier, is thermal, but it's the ground state. And then the highest state is the ground state of minus H naught. But all the ones in between, in a thermal state, the spin would have some probability of being aligned with the field and some probability of being anti-aligned with the Boltzmann probabilities. But in all the eigenstates, it's just 0, 1, right? So every spin is acting like it's 0 temperature, even though some are aligned and some are anti-aligned. So the eigenstates are not thermal. And of course, the system doesn't thermalize. It's got an enormous number of conservation laws. And let me just show you that. So what happens? Each spin just Larmor processes about its field. No energy is being transferred between spins. It's a trivial system. but it has a certain structure, which I'm going to point out. So let's define operator tau n, which is, do this the way I want to do it here, right? So we take a unit vector along the field, so that's hn hat dot sigma n, right? And this has eigenvalues plus or minus 1 because that's a unit vector, right? This is the unit vector pointing along the field. These are all conserved, right? So this Hamiltonian has the property that all tau n's commute with h naught, and they commute with each other, right? So this is just, one component of each spin. The one that's along the field is conserved. That's this. These are all equal to 0. And since they're on different spins, that's n and m, they commute with each other. So this is a way of saying this is an integrable system. We've got a complete set of conserved quantities, and the conserved quantities are all localized. So this is an operator, right? This tau n is an operator. It's a localized operator, localized to a single spin. It's conserved, and we have a complete set of them, right? It's a trivial model, but it has a certain structure, a complete set of localized conserved operators. And that is the structure of the many-body localized phase to the extent we understand it, which I think we do. There goes the lights again. Okay, so now what we're going to do is add interactions. Going to add weak interactions. Actually, let me just do it. Start another board. I'll keep this Hamiltonian here. Keep this here. Here. Okay, so we're going to add weak interactions, and I'm going to do it in one dimension because it's really only in one dimension with short-range interactions that the MBL phase is believed to actually exist as a stable phase. So we're going to add weak interactions. So H is now H naught, which is just all these spins in their random fields. These are all random. Actually, they don't have to be random. They could be in a quasi-periodic pattern, but I don't want any degeneracies. So every H sub n has a different magnitude than all the others, right? So they could be the same orientation, but I don't want, so they're drawn from a distribution which is continuous. So somehow they're set up so no two of them are of exactly the same magnitude. And that can happen due to random numbers from a continuous distribution or a quasi-periodic pattern or things like that. Okay. So now I'm going to add my interactions. Weak coupling constant G that we can make small. And then I'm just going to put in nearest neighbor interactions. So n equals 1 to n. Some coupling J sub n, which couples spin n to spin n plus 1. This could just be any old coupling that's generic, just a random matrix in this four-dimensional Hilbert space. Nearest neighbors, right? And what happens is, what Basco, Elena Altschiller argued, not for this specific model, but their arguments apply to this model, is that this structure of many-body localization survives turning on a weak enough interaction. And then John Embry proved that he had to make one assumption, which nobody thinks is false, but he couldn't prove it. And other than that, it's a mathematical proof. He proved it for one dimensions with short range interactions and weak enough couplings. And so what we so the result is for G small enough, MBL survives. And what that means is that how does it survive? So we've got these conserved operators. We still have the conserved operators, but now we have some interactions. So we've got to take our conserved operators and we've got to dress them just like you would dress quasi-particles in Fermi liquid theory when you added the interactions. So we dress the operators. So tau n goes to this here. Let's call this tau n naught for h naught. So it goes to tau n naught plus g times some stuff, which is just short range spin-spin terms with an index 1, and then g squared times some more stuff with subscript 2, etc. So you dress it in order to preserve these commutation relations. Well, so now we just want to have it commute with h. So we want to dress these operators to keep them commuting with each other and with the Hamiltonian. And basically what Imbri showed is if G is small enough, you can do this and this series converges, right? In one dimension with short range interactions. So that's the structure of the MBL phase. It's so, and right. This series converges and all the corrections we put on are also localized operators localized near the original spin inside some envelope that's decaying exponentially like usual in Anderson localization, right? So it's not strictly localized on one site, it's localized within an exponential envelope.
So David,
in NBL, we don't localize the wave function. So in the usual single particle Anderson localization, it's the eigenstates that are localized in real space. In the many-body problem, the eigenstates have a value everywhere because you have to give every spin a wave function. What's localized isn't the eigenfunctions, it's the conserved operators.
So David, the question I always have about this is, you could wonder, like, as you're tuning away from the idealized paramagnetic limit, so the ideal Anderson insulator, you know, what is the character of the distribution of locality? Like maybe there's an average localization radius.
Yeah.
But if the distribution itself becomes very broad, then the question is, you know, is that all the same phase, or could something else happen?
Yeah. Well, so
and is that controlled?
What happens is, yeah, all these statements are for almost all, right? So almost all of them decay exponentially. The ones that don't, their probability, you know, the number of them that, right? Say we have an operator and we go to distance r and ask how much it's decayed. So they will typically decay exponentially with r. But then there will be some that didn't decay. But the fraction of the operators that didn't decay will decay exponentially with r, right? So you do have enormously broad distributions, and you have rare cases of operators that don't decay. These are the rare regions, but they occur with a probability that's exponentially small in the range, right? And as long as you don't need everything to decay exponentially itself. You need the exceptions to be a rare set that decays exponentially with the range, right? And that's really the way it goes. Yeah, and we've been exploring that, you know, finding these enormous, these rare events are of interest, as you know. So this is like Fermi liquid theory, right? In Fermi liquid theory, you start with non-interacting electrons, you get a Fermi surface, you have conserved particles, and then you add the interactions and you dress your particle operators to become quasi-particle operators. Now, in that case, you don't insist on this, right? You don't insist that your quasi-particles have an infinite lifetime, whereas here we do. So the true many-body localized phase is stronger than, the dressing is better than in Fermi liquid theory. It's not just that they almost commute, but have a finite lifetime. Here we ask them to commute. And not only, in Fermi liquid theory, it's only the ones near the Fermi surface that have a long lifetime. The ones which are way away from the Fermi surface are a very short lifetime. Whereas here we're asking them all to have an infinite lifetime. So it's a much stricter thing. what we found recently is so for small enough G, you have this structure in a one-dimensional model like this. There's a phase transition, and then you lose it. And you're no longer in the MBL phase where these commutators are 0, right? But you end up going into another phase, which still looks very much many-body localized, and that's more like the Fermi liquid, where the commutators in the Fermi liquid, these commutators are not 0, they're just small compared to microscopic scales. And so let me just finish with the current version of the phase diagram of an MBL model like this. So here's the non-interacting problem. Here's some critical point. Here's the MBL phase, where we have this structure with the commutators being 0. But then what we've discovered quite recently is out a large factor stronger interaction, there's a crossover. And so there's an intermediate regime here, which I'm calling pre-thermal MBL. So it has this structure, but with the commutators very small, so that on the size scales you can study in exact diagonalization numerics, or that you can study in experiment, you don't see the relaxation. The commutators are 0 to the precision you can do. But we have good theoretical arguments that ultimately, in the limit of an infinite system and infinite time, it's actually going to thermalize. And so there's a big, so this is easy to see because you do experiments or diagonalizations. So here it thermalizes, you see it thermalizes, here you don't. And you see this crossover. But now we figured out a way to estimate where this is. And we found it's not near here. We used to think it was, somewhere right near here, but we found it's actually much further on. And it opened up this great big intermediate regime, which we're trying to understand this stuff better. This part we think we understand pretty well, but this part and this part less so. Partly because we didn't even realize this part was so big, so we didn't even focus on it very much. Yeah, so that's sort of where we are in the study of MBL. Now, if you go above 1 dimension, this GC goes to 0, the phase goes away, but this pre-thermal regime is still there. So when people study many-body localization in 2 dimensions, they're not looking at a phase transition. They're just looking at a crossover from a regime that thermalizes to one that doesn't on the timescales of their experiment or their numerics or whatever. And it's more like a structural glass transition from a liquid to a glass, where there just may not be an underlying phase transition at all, right? And so that's sort of where we are. So yeah, maybe just as what did I talk about? To summarize, I told you about quantum thermalization, our current understanding of what are the issues there, and then a little bit about many-body localization. Please, sorry to run over a little bit, but we had some questions and we can have some more.
Fantastic. Well, I'll allow people to unmute themselves, but maybe just raise hands so I could call people's question. Maybe it will be more orderly. So, Caden, go ahead, please. And then Mudit.
Well, I was just clapping and I've asked some questions. So I do have questions, but why don't we let Mudit go first?
Okay. Mudit and then Guido.
All right, thanks. So yeah, I just had a quick question on this window of pre-thermal MBL.
Yes.
So presumably, and constraining myself only to 1 dimension for the moment, this window must depend, I'm thinking, on the type of interaction that you have, right? The JC that you've written on the board.
Yeah,
Yeah,
definitely.
So then you're restricting yourself to some particular type of interactions, which does allow you to have a big gap between GC and crossover.
Well,
Or is
if
that
we
not?
knew how to pick some interactions such that this was close to each other, we would love that.
So exactly. So that's what I want to
Seems to be
understand.
this is something that's new. We've looked at a few models. A big difference here seems to be the generic behavior. We don't have, we don't really know how to manipulate that. You're right. If you could think of a model where you could make a good argument that this was much smaller in one dimension with short range interactions, I would be very interested, because that would be very interesting for us to look at.
So basically you're saying that like you've looked over a lot of short range interactions. So J sub n.
No. We've looked at two models seriously.
Two models, okay.
Because it's a fair amount of work.
Sure.
To do this well is challenging numerics, and we're actually just figuring out, trying to do it better than we've done it on the models we've done. So we're still not completely satisfied, and that we've done the best job we can do on the models we've done, and so we're working on that first. The thing is, the relaxation times here are so slow that you run up against double precision round off error long before your systems get too big to diagonalize. So we, and the problem is, double precision is super fast on the computer because it's in the hardware. But if you want to go beyond double precision, it's not in the hardware, and you just take an enormous hit. And so we're trying to figure out what's the best way to do this with precision beyond double precision. Can we get a little further than we were able to get? So it's an interesting case where, you normally, when you're doing exact diagonalization on quantum systems, you're stopped by the Hilbert space blowing up, right? But here we're stopped even before the Hilbert space gets too big, just because the relaxation rates are getting so small. We run into problems around 12, 13 spins with double precision. And that's a small system. So it's it's something, what we have is a bound on this. It might be a little further on than what we think it is. And so it's all new, and we haven't yet surveyed a lot of models.
Guido, go ahead.
Thanks, David. You said that for higher dimension, this true MBL phase goes to 0. Is that like a proof, or is?
It's a very good argument. So I've been taught, right? That's a statement about systems with randomness. So when you have randomness in here, or here, then you have rare region effects, which is, if you take a very large system, there will be a patch in that system where, just by chance, the randomness is weak and it locally thermalizes. Instead of being down here, locally it looks like it's up here and it thermalizes. Just by chance. It happens with a very low probability, but in an infinite system, you will find such patches. And those patches are very dangerous, right? Again, as a quantum experimentalist, when you have so the MBL phase is coherence, and this is decoherence. And when you have a competition between those two things, the decoherence totally has the upper hand. So an infinite MBL system with a little tiny island that's thermalizing, the little tiny island that's thermalizing can win, because it just entangles the nearby spins, and that makes a bigger bath, and then it entangles some more spins, and it just grows and entangles the whole system, right?
But experimentally, is there any way that any observable that differentiate between MBL phase and pre-thermal MBL that can be, practically?
This is going to be
like entanglement entropy, for example, grows logarithmically in the pre-thermal MBL, or it doesn't? Like, there's some signature that.
Well, let me tell you the calculation I did, which we did. Sorry, this is I should put some names down. So what we're talking about now is work where my student Alan Morningstar is the first author. Another student in Germany, Colmenares. I always forget how to spell his name. David Lewitz, who's in Germany. Edgar Germani, who's in Stanford, and me. So it's a 5-author paper posted 3 months ago. But we, and then there was a second paper by Dries Sells, who pointed out a better way to do this calculation, which is correct. And now we're trying to do it well. With our work, we don't quite trust his numerics because of this precision issue. So that's why we're being super careful about this precision issue I was talking about. And so what that calculation is you take a small system, spin 1 here, spin L here, so it's of length L, and you couple this to an infinite bath, which is an infinite temperature bath. But you couple only the first spin to it. And then you calculate the relaxation rate of the farthest spin and look at this as a function of distance. And so that's an open system calculation, which one can do if the chain is short enough. Although we run into, like I say, we run into these precision limitations before we run into Hilbert space limitations. But one can do such setups in the lab as well. You can't really make an infinite bath. Actually, maybe you could, right? If you really could set it up to couple only the first spin to the environment.
Yeah, I mean,
the whole environment, but only the first spin, and control that. And then you look at the relaxation of this spin. So that would be a way in the lab to do what we did to calculate this. So it's not out of the question. It relies on some theory that says, what is the criterion for the difference between this and this, right? It's that this decays with L fast, it decays exponentially. Basically what the critical value, so GC is this relaxation rate decaying as 4 to the minus L. So when the relaxation rate of this spin, 1 spin per unit length, decays as 4 to the minus L at large L, that's where this instability happens, right? But that's theory. So you're not really directly observing the difference between this and this. You're using the modeling and the theory to estimate from this relaxation rate where that boundary is. And that's what we're doing in the numerics as well. We don't explicitly see that this ultimately thermalizes and this doesn't. We're relying on
I see.
theory.
So David, allow me to make a practical suggestion. Because I don't want to interrupt the discussion live, and it seems to be people have, we have a few more questions. But allow me formally to thank you. But tell us first, do you have 5 more minutes to answer a few more questions?
Yes. No, I am happy to stay, but anybody who doesn't want to stay is free to leave, of course, right? I don't even have to say that, right? It's easy to leave, right?
That is true. It is Zoom. But yes, allow me to formally thank you, David, for an awesome talk. I'm going to stay. I'm not leaving, but please, whoever, don't feel obliged to stay more. And what I will do, I'll voice a few questions that were in the chat, and a couple of more people can still have their hands raised. Thanks again, David. And allow me to